Normandy, July 1944. The air trembles with the echo of distant artillery. A German Panzer IV idles at the edge of a ruined French village, its crew scanning through the periscope slits, searching for movement beyond the smoke. The gunner squints. A shadow moves between the hedgerows. Through the haze, the unmistakable silhouette of an American Sherman tank emerges, mud splattered, and advancing steadily through the fields. The Panzer gunner loads an armor-piercing round, breath held tight. The shell fires, a flash, a thunderclap, and slams directly into the Sherman's front plate. But instead of cracking apart or sending fragments inward, the round glances off in a shower of sparks, leaving behind only a shallow dent and scorched paint. The American tank keeps moving, its welded hull gleaming under the morning light, seamless, solid, as if made from a single block of steel. Inside the Panzer, disbelief spreads. The commander mutters under his breath, "Das ist unmöglich!" They had never seen armor like this before. And from that moment on, the myth of American fragility began to die in the eyes of the German tank corps. When the Second World War erupted in 1939, armored warfare was still evolving, an art defined by doctrine as much as by metal. Every major nation had entered the conflict with its own idea of what a tank should be. For Germany, the answer was speed and precision. Fast, aggressive machines that struck hard and vanished before the enemy could react. For Britain, tanks were divided between infantry support and cruiser designs, each serving a different battlefield role. But in the United States, armor had taken a quieter path. The interwar years had left the American Army with limited funding and outdated equipment. When Europe descended into chaos, the U.S. possessed fewer than 400 tanks, most of them light, thin-skinned, and riveted together using methods more suited to bridges than battlefields. Those rivets, seemingly harmless, would soon prove fatal. In early war campaigns, particularly during the Philippines and North Africa, American tank crews learned the hard way that riveted armor could become a deadly liability. When struck by enemy shells, the steel rivets didn't always fail cleanly. Instead, they popped loose, ricocheting inside the crew compartment like bullets. Soldiers who survived called it the shotgun effect. Meanwhile, across the Atlantic, German engineers had refined the art of tank construction to a near science. The Panzer III and IV, mainstays of the Wehrmacht's early conquests, used hardened rolled armor plates connected by precision welding and interlocking joints. The seams were smooth, strong and uniform. No gaps, no rivets, no weak points. To the Americans studying these machines, captured in North Africa and later in Italy, it was a revelation. By 1941, the United States had joined the war, and with it came an industrial mobilization unlike anything the world had seen. Factories that once built cars, tractors, and locomotives were retooled to produce tanks by the thousands. But building tanks at that scale meant confronting a question not of design, but of method. How could America mass-produce armored vehicles that were fast, strong, and easy to repair, without sacrificing battlefield resilience? The answer lay not in Europe's foundries, but in America's own steel workshops. Long before the war, American industry had been quietly perfecting a technique once considered too experimental for combat vehicles: electric arc welding. Unlike traditional riveting or bolting, welding fused two pieces of metal into one. Done correctly, the result wasn't a connection, it was a single continuous structure. The advantages were immense. A welded hull weighed less than a riveted one, required fewer components, and offered greater protection from spalling when hit. But in 1939, welding large armor plates was still considered risky. The process demanded precision, consistent heat, and expertly trained labor. Any flaw could lead to cracks, distortions, or weak seams. In Detroit, engineers at General Motors, Ford, And Chrysler's newly formed Detroit Tank Arsenal began experimenting with large-scale welding for tank production. Under the leadership of the Ordnance Department and engineers like Robert Patterson and Harold Young, America invested heavily in developing new welding techniques, submerged arc welding, automatic flux feed systems, and heat-treated rolled homogeneous armor. By 1942, these efforts bore fruit. The M4 Sherman, America's new medium tank, rolled out of factories with a fully welded upper hull. Smooth, clean, and remarkably strong. Early prototypes had still used riveted lower sections, but as production advanced, welding took over completely. The technique not only made the tanks lighter and stronger, it made them faster to build. The results shocked even the engineers themselves. Welded hulls withstood repeated test impacts without catastrophic failure. Cracks that appeared in prototypes were analyzed, corrected, and prevented with improved preheating and stress relief methods. What had once been an experimental gamble now became the standard of wartime production. And when those first welded Shermans crossed the Atlantic, their performance on the battlefield began to rewrite reputations. German Panzer crews, long accustomed to seeing enemy armor crumble under high-velocity shells, found themselves staring at tanks that could take punishment and keep fighting. It wasn't that the Sherman was invincible, far from it. Its armor could still be penetrated by the 75mm and 80mm guns of German tanks. But its construction, the way its hull absorbed and redirected impact, the way its weld seams held together under fire, made it far more durable than it appeared on paper. The secret was not in the thickness of its armor, but in how it was joined. And as the American war machine began to reach full production, that secret would soon define the industrial battlefield of the 20th century. By 1943, the transformation of American armor was complete. The U.S. had mastered not only the art of building tanks, but the science of building them fast. From the sprawling assembly lines of the Detroit Tank Arsenal to the steel mills of Pennsylvania, thousands of M4 Shermans, M3 Lees, and later M26 Pershings rolled out month after month. It was an achievement that stunned even America's allies. But the true secret behind this mechanical flood wasn't just mass production. It was consistency. Welding allowed American factories to assemble tanks with precise uniformity. Each hull, each turret, could be duplicated with minimal variation, unlike the hand-fitted riveted constructions of earlier years. For a global war that demanded logistics and replacement over perfection, this reliability was gold. The German army, on the other hand, had moved in a different direction. After years of dominance in the early campaigns, its tank design philosophy had evolved toward power and complexity. The Panzer IV had given way to the Tiger I, and soon after, the Panther, formidable machines with thick, sloped armor and devastating high-velocity guns. Yet their production came at a steep cost. Each Tiger required over 300,000 labor hours to construct. Every weld was hand-inspected, every component machined to perfection. Where Germany produced a handful of Tigers each week, America built hundreds of Shermans. The difference was not just industrial capacity, it was method. American welded armor construction required fewer man-hours, fewer materials, and fewer failure points. Germany's intricate manufacturing, though technically superior in craftsmanship, was strangled by its own precision. This contrast became painfully visible on the battlefields of North Africa. When American M4s joined British forces against Rommel's Afrika Korps in late 1942, the Germans initially dismissed them as just another Allied machine. But soon, reports filtered in describing tanks that could take glancing hits to the hull without catastrophic failure, even when the armor was thinner than that of a Panzer IV. The reason, German engineers would later note, was the absence of rivets. In a riveted tank, even a non-penetrating shot could send shards of metal scything through the interior, killing or maiming the crew. In a welded tank, that energy dissipated differently, spreading across the armor plate and weld seams, often sparing the crew from the deadly spall that haunted earlier designs. For the men inside, this meant survival. And survival meant experience, adaptation, and morale. By the time the Allies landed in Normandy in June 1944, the U.S. Army's armored divisions had turned this engineering advantage into doctrine. Tanks were not built to outgun or out-armor the enemy. They were built to stay in the fight, to be repaired quickly, and to return faster than the enemy could replace theirs. The welded hull made this possible. When a Sherman took a direct hit, mechanics could patch or re-weld damaged sections on the field using portable equipment. A riveted tank, once its structure was compromised, was often beyond saving. American maintenance crews, known as the grease monkeys of the front, became the unsung heroes of the armored war, keeping the welded fleet operational with astonishing speed. German field reports began to reflect this frustration. Tank commanders described American armor as stubborn, noting that enemy vehicles remained serviceable after multiple engagements. Engineers in the Wehrmacht's technical branches examined, captured Shermans, and documented the efficiency of their welded seams. One 1944 report from the Heereswaffenamt, Army Weapons Office, noted that the Americans had achieved industrial perfection through welding, a level of consistency Germany could not replicate under constant bombardment. Even the Soviets, masters of mass production in their own right, took note. American Lend-Lease tanks arriving on the Eastern Front impressed Red Army mechanics with their ease of repair. The U.S. had proven that modern warfare wasn't just about firepower. It was about industrial resilience. Behind every welded hull lay an invisible army. Thousands of American welders, men and women, trained under government programs that turned factory workers into precision craftsmen. Using new automated systems developed by Union Melt and Lincoln Electric, they achieved welds so uniform that defects dropped to record lows. The process was so efficient. The post-war engineers would later use these wartime welding methods to shape the future of industrial steelwork. From bridges to ships to skyscrapers, by the end of 1944, German crews could no longer afford to underestimate the soft American tank. They had learned, often through bitter experience, that the M4's armor design was not a weakness of thickness, but a strength of construction. What began as an engineering experiment in Detroit had become a battlefield revelation across Europe, and soon it would collide with Germany's most feared machines in the decisive armored duels that defined the Western Front. The difference between riveted and welded armor seems, at first glance, like a technical footnote, but in the world of armored warfare, it was revolutionary. A riveted tank was built like a ship, steel plates joined by bolts and rivets hammered through pre-drilled holes. The method was sturdy but flawed. Each hole weakened the armor's integrity. Each rivet became a potential fragment when struck. It was a system born of an older industrial age, when factories were optimized for mechanical assembly, not precision welding. Welding changed all of that. In a welded tank, the armor plates were joined edge to edge, the seams fused with molten metal until they became a single continuous mass. The stress of impact no longer concentrated around rivet holes. It distributed evenly across the welded frame. This made the tank not just stronger, but more resilient to repeated shock. American engineers also discovered another benefit: efficiency. A welded hull required less internal framing, reducing weight without sacrificing protection. That extra ton or two, saved from unnecessary steel, could be reallocated to thicker armor or a larger gun. By 1942, the Ordnance Department had commissioned massive studies into weld quality and heat treatment. Laboratories in Aberdeen, Maryland, tested new steel alloys under high-velocity impact. Every defect, every crack, every brittle seam was studied and corrected. The outcome was a standardized process that could be applied in hundreds of factories nationwide. What made America's approach unique wasn't just technical innovation. It was scale. Welding wasn't performed by a handful of experts in a single plant. It was industrialized. Automated welding machines, operated by trained men and women across the country, produced thousands of identical hulls with microscopic precision. German engineers, who prided themselves on craftsmanship, were astonished when they examined captured Shermans. The seams were clean, uniform, almost artistic, but done at a pace Germany could never match. It was, as one German officer later described, the difference between an engineer's workshop and an industrial civilization. For the first time in military history, metallurgy itself had become a weapon. On the battlefield, these invisible weld seams translated directly into survival. In North Africa, where dust and shrapnel filled the air, American tank crews quickly noticed that welded hulls suffered less from spalling, the lethal shower of metal fragments that often killed crews even when the armor wasn't penetrated. The smooth, fused surfaces absorbed kinetic impact without sending rivets flying. When the Shermans rolled into Sicily and later Normandy, their crews fought in environments where every second counted. Under fire, a riveted tank could become a coffin. A welded tank might stay mobile long enough to fire back or retreat. German gunners were initially confident. The Sherman's armor was thinner than a Tigers or Panthers. But what mattered wasn't thickness alone. Many German rounds that struck the Sherman's curved welded hulls at oblique angles failed to penetrate, glancing off in bursts of sparks. Reports from the 12th SS Panzer Division in Normandy note that enemy tanks withstand side impact better than expected, likely due to hull structure. Meanwhile, American maintenance units exploited another tactical advantage of welded construction: repairability. Portable welding kits followed armored divisions into combat zones. Damage that would have sidelined a riveted tank for weeks could be fixed in a day. Crews began to trust their machines. They learned that even if the hull was scorched, dented, or cracked, the seams would hold. That confidence changed how they fought. Tankers advanced boldly, coordinated closely with infantry, and absorbed punishment that would have unnerved earlier generations. Welded construction didn't make them immortal, but it made them reliable. And reliability wins wars. For the Germans, this consistency was baffling. They had been taught that quantity was the enemy of quality. Yet here was a tank built in massive numbers, showing no sign of weakness in its design. Even when captured or burned out, Shermans showed remarkable structural integrity. The Germans could destroy them, but they couldn't make them fail. As the front lines shifted and the Allies advanced toward the Siegfried Line, one question began to trouble German field officers and engineers alike. How had the Americans managed to build something so simple and yet so effective? That question led to a deeper examination, not of tanks, but of the minds and systems that created them. Inside a tank, design becomes life or death. For the 5 men of a Sherman crew: commander, gunner, loader, driver, and assistant driver. Every weld, every joint, every vibration under fire was personal. American crews often named their tanks, painted them with humor, carried home photos taped near their periscopes. The welded armor gave them a sense of safety that statistics couldn't measure. Survivors recalled how the hulls flexed but never broke, how impacts would echo like thunder but leave them breathing. For German crews, the first encounters were unsettling. They had expected to face weak, clumsy machines, and instead found tanks that refused to die easily. Accounts from panzer units near St. Lo describe Yankee tanks that burned slow, that would not break apart. The precision of the welds and the toughness of the steel created an impression of almost industrial invincibility. This psychological shift mattered. Confidence is a weapon. Doubt is a wound Every time a German round failed to cripple a Sherman, morale shifted slightly in the Allies' favor. Every time a welded tank returned from repair, soldiers saw proof that industry, not just courage, could win battles. By mid-1944, even veteran German crews began to whisper a quiet respect for the machines rolling toward them. And behind that steel confidence was a secret most of them never understood: that the weld, invisible and silent, had already reshaped the war. The welded armor revolution didn't just change the way tanks were built, it reshaped the way armies thought about them. Before America's entry into the war, armored doctrine was divided between competing philosophies. The Germans treated their tanks as instruments of lightning warfare, fast, coordinated, and lethal in combined arms formations. The Soviets emphasized numbers and shock. The British focused on specialization, building different tanks for different battlefield tasks. The Americans, however, adopted a doctrine of practical flexibility. Their leadership, men like General Leslie McNair, General Jacob Devers, and General George S. Patton, understood that tanks weren't only machines of destruction. They were tools of endurance. The goal was not to field the most fearsome individual tank, but to ensure a constant, self-sustaining flow of armor that could fight, be repaired, and fight again. This philosophy was only possible because of the welded hull. It allowed tanks to be repaired in the field without major reconstruction, which aligned perfectly with the American doctrine of mobility. A division could stay operational even under heavy losses because its equipment was repairable. Leadership valued that more than raw armor thickness. When Patton's Third Army surged through France in the summer of 1944, speed became the weapon. Shermans rolled hundreds of miles with minimal downtime, supported by mobile workshops that welded and patched armor overnight. Patton himself famously remarked that "My men can outfight, outmove, and outlast any tank army on Earth." What made that boast possible was not mystical bravery. It was industrial design. German leadership, by contrast, was trapped in a paradox. They built tanks that were masterpieces of engineering but nightmares of logistics. Hitler's fascination with technical superiority led to constant changes, new models, new armor compositions, new specifications that slowed production and repair. The Tiger and Panther were formidable, but their complexity made them fragile. When Germany studied captured Shermans, their officers understood too late what America had achieved. A tank that wasn't the best, but was good enough everywhere that mattered. Doctrine and engineering had fused into one philosophy: victory through reliability. To the German engineers and tank commanders who encountered welded American armor, the reaction was a mixture of disbelief and reluctant admiration. At first, reports from the field seemed almost dismissive. The Sherman was mocked for its high profile, its gasoline engine, its thin armor. But by 1944, after countless engagements across Normandy and the Ardennes, those same reports began to change in tone. Captured vehicles were examined by the Wehrproof 6, the Wehrmacht's armament testing division. Their engineers discovered that the American hulls were made from rolled homogeneous armor with uniform carbon and manganese content, heat-treated to exact tolerances. The weld seams showed almost no porosity, an indicator of near-perfect control of temperature and feed. In contrast, Germany's own factories were under siege. Allied bombing had crippled the steel supply chain, forcing engineers to use substitute alloys. Welding quality deteriorated. Some late-war Panthers exhibited brittle seams and microfractures from rushed construction. One captured report from a German maintenance unit noted, "American tanks appear of lower material thickness, but show superior resistance to cracking." Welding of hull seams and turret joints displays industrial precision impossible under present conditions. The irony was bitter. Germany, once the standard-bearer of engineering precision, was now outmatched not by superior craftsmanship, but by standardization. Welding had given America a new kind of strength, reproducibility. Each tank leaving the line was nearly identical to the last. Every repair crew, every mechanic, could apply the same procedures with predictable results. The system was mechanical, mathematical, and devastatingly efficient. Even German tank aces like Otto Carius and Ernst Bachmann, who respected no enemy machine lightly, acknowledged that the Shermans' numbers and endurance made them formidable. Each destroyed tank seemed to be replaced almost instantly, its successor rolling out of the same industrial mold. To Germany's engineers, that seamless armor was more than metal. It was a symbol of America's industrial discipline. A precision not of a craftsman's hand, but of an entire nation's machinery working in harmony. Every technological leap in war carries a human echo. The welded armor wasn't only a material improvement, it was a psychological one. For American crews, it meant confidence. They could charge forward, knowing that even if struck, their tank might hold long enough to save them. That sense of survivability bred aggression and unity. Tankers developed deep bonds with their machines, not because they loved them, but because they trusted them. For German crews, the emotional effect was opposite. Facing endless columns of Shermans that refused to stay down wore on morale. Each glancing round, each failed penetration, chipped away at their aura of superiority. The Tiger and Panther crews knew they were technically superior, but they also knew that superiority was meaningless against a force that could replace its losses before nightfall. The more they studied American armor, the more unsettling the realization became. The Allies were fighting not with individual tanks, but with an industrial ecosystem. The welded hull symbolized that machine, one that never slept, never broke, never ran out of steel. A German veteran later summarized it simply, "We fought soldiers, but behind them stood factories. And behind the factories stood a method." It was a truth that transcended armor thickness and gun caliber. America's real weapon was process, and soon that process would be tested in the crucible of direct confrontation, where German engineering and American industry would finally meet, face to face, across the smoke and fire of Europe's bloodiest battlefields. Normandy, July 1944, the Bocage country. The fields of northern France had become a maze of hedgerows, stone walls, and narrow lanes. Here, the tank was not a blunt instrument of terror, but a weapon of patience and precision. And it was here, amid the claustrophobic green corridors, that the true test of American welded armor would come. After D-Day, the German army regrouped quickly. Panzer Lehr, 2nd SS Panzer, and elements of the 12th SS Hitlerjugend Division entrenched themselves behind natural barriers. Their Tigers and Panthers dominated open ground, their guns calibrated to tear through Allied armor from half a mile away. For the Americans, every advance came at a cost. The Sherman, lighter and armed with a smaller gun, was outmatched in raw firepower. Yet, the welded armor began to reveal its advantage not through invincibility, but through endurance. During one such encounter outside the village of Saint-Lô, a column of Shermans from the U.S. 3rd Armored Division came under ambush from a group of concealed Panthers. The first American tank took a direct hit to the glacis plate. A clean strike from an 88mm round. The impact shook the entire hull, but instead of splitting or bursting, the weld seams held firm. The plate bent slightly, cracking around the edge, yet the crew survived. Within seconds, the tank reversed, smoke billowing, still operational. Nearby, the second Sherman took a glancing shot along its welded side armor. Sparks flew, the shell ricocheted upward, and the tank pivoted to return fire. In moments like these, the difference between riveted and welded construction wasn't abstract theory. It was measured in human heartbeats. The The Germans, expecting explosions and disintegration, saw their shots fail to produce the chaos they once relied upon. The American tanks moved as a unit, coordinated, absorbing punishment, and continuing the advance. When one was disabled, recovery crews arrived within hours, welding torches flickering through the night, patching the same hulls that had been targeted only hours before. By the next morning, some of those same Shermans were back in formation. For the panzer crews, it was a psychological blow. Their doctrine depended on fear, on the sight of enemy armor burning. But these machines refused to die dramatically. They burned slow. They stayed intact. They came back. A German field report from the 2nd SS Panzer Division, recorded in July 1944, noted, "Enemy armor exhibits unusual resistance to fragmentation. Welded construction appears to prevent hull separation and internal ricochet. For the Americans, that unusual resistance was life itself." The U.S. Army's Armored School later analyzed dozens of battle-damaged Shermans from the Normandy campaign. The conclusion was consistent. Welded hulls suffered fewer catastrophic crew losses than earlier riveted models. Even when penetrated, the structural cohesion prevented the armor from shattering inward. Meanwhile, field workshops, often working under artillery fire, had developed a rhythm. Crews trained to cut, align, and re-weld armor plates on site. Damaged hulls were reinforced with salvaged sections, the repairs blending seamlessly with the original weld seams. No nation in the war repaired its tanks faster. In the chaos of the hedgerows, this adaptability became decisive. Shermans could be recovered, patched, and sent back into battle within a day. German tanks, once hit, were often lost, too heavy to move, too complex to repair. Even the Panthers' sloped armor, so feared in theory, was betrayed by its rushed welding in late 1944. Cracks appeared along its seams under heavy stress. Some German crews complained of hull fractures during long marches, a sign of metal fatigue worsened by inconsistent welds. As the Allies broke through Saint-Lô and pushed toward Coutances, the contrast became undeniable. The American tanks were not the most powerful. They were the most sustainable. Every night, under the low hum of generators and the hiss of acetylene, welders kept the divisions alive. Their sparks lit up the fields like fireflies, a mechanical constellation following the army across France. For the first time in the war, German tank crews realized that even their technological superiority could not overcome America's mastery of method. They had designed machines to win battles. The Americans had designed a system to win wars, and as the front lines moved east toward the German border, that difference, invisible to the naked eye, would become the deciding factor in Europe's armored war. The Ardennes, December 1944. The Battle of the Bulge. The last great gamble of the German army had begun. Snow blanketed the forests, muffling the roar of engines. From the east, the ground trembled as columns of Tigers and Panthers surged forward, their armor gleaming beneath the pale winter sun. Hitler's plan was bold. A surprise offensive through the Ardennes, driving a wedge through the Allied lines and reaching Antwerp, caught in the onslaught. Were units of the U.S. 7th Armored and 10th Armored Divisions, men who had learned to trust their machines through bitter months of fighting in France. Their Shermans, with welded hulls patched and repatched since Normandy, waited in the frozen villages of Belgium and Luxembourg. When the first German shells tore into the snowbound towns, the Shermans met them head-on at Bastogne, Clairvaux, and Saint-Vith. Tank duels erupted in white silence. The Panther's 75mm gun punched through steel with terrifying accuracy. But the American tanks absorbed blows that earlier generations could never have survived. Weld seams held even when plates bent inward, the hulls groaning but intact. In one engagement near the village of Neuville, A Sherman of the 10th Armored Division took 3 hits in rapid succession. 2 rounds failed to penetrate, glancing off its glacis at shallow angles. The third punched through, killing the driver. Yet the hull did not split. The rest of the crew bailed out and lived. Hours later, an ordnance team dragged the tank back under cover, replaced the damaged plate, and had it operational within a week. That cycle, hit, recover, repair, return, defined the American experience in the Ardennes. German tankers were astonished to see Shermans reappearing after battles where they had been supposedly destroyed. In interviews recorded after the war, several Panzer veterans recalled their disbelief. "We hit them again and again. They came back the next morning, always more of them. Welded, patched, alive again." The explanation was mechanical, not mystical. Welding allowed modular repair. Entire armor sections could be cut and replaced in the field, maintaining structural integrity. Riveted tanks, by contrast, often warped beyond use when struck. The U.S. Army's mobile maintenance units, the unsung tank doctors, kept divisions rolling where German formations stalled. By mid-December, the German advance began to lose momentum. Fuel shortages, icy roads, and relentless counterattacks bled away their strength. American armor, though battered, remained cohesive. The Shermans' welded hulls, able to shrug off near misses and resist cracking in the cold, endured where heavier German machines faltered. Even the elements favored the Americans. The extreme winter cold exposed weaknesses in German metalwork. Weld seams on several Panthers and King Tigers developed stress fractures as temperatures plunged, a result of uneven wartime alloys and rapid welding under bombed-out factory conditions. American tanks, built under consistent quality control, showed far fewer such failures. When skies cleared and Allied air power returned, the outcome was sealed. The German offensive collapsed, and the Wehrmacht's remaining armor was forced into retreat. Many tanks abandoned, frozen or immobilized by mechanical failure. After the battle, captured German officers toured American repair depots near Liège. They were stunned. Hundreds of tanks, some with visible scars and weld patches, were lined up in various stages of repair. Electric arcs flashed in the cold air as mechanics welded hulls, sealed cracks, and reinforced seams. To the Germans, it looked less like a repair yard and more like a living organism, a mechanical ecosystem feeding itself. Colonel Hans von Luck, a panzer commander who later wrote of the campaign, described his reaction in one line. Their strength was not in the tank itself, but in how quickly they made it new again. By the time the snow melted, the outcome was no longer in doubt. German tank crews could no longer rely on quality to offset quantity. The American welded hull had proven itself not only as armor, but as a philosophy. It was the triumph of process over perfection, of mass efficiency over mechanical elegance. The Tiger and Panther might still inspire fear, but the Sherman, rebuilt, rewelded, relentless, had become the instrument of inevitability. And in that realization, as the wreckage of both armies froze across the Ardennes, the German Tank Corps finally understood what their engineers had hinted at months before. They were not fighting against machines, they were fighting against a method. Spring, 1945. Across Europe, the war's metal skeletons lay scattered, the carcasses of Tigers and Shermans alike, half buried in mud and snow. But as Allied forces surged eastward toward the Rhine, a quiet truth had become impossible to ignore. America's tanks, though outgunned, had outlasted. The reason was not hidden in a factory secret or a classified blueprint. It was visible in every scorched hull, every welded seam. When U.S. Army engineers and ordnance officers compiled post-battle reports, they found something extraordinary. Tanks built with welded armor had suffered fewer catastrophic failures than their riveted predecessors. Even when penetrated by German shells, weld seams rarely split. Internal explosions were less violent. Crews, more often than not, survived. In March 1945, the U.S. Army's Ordnance Department published its Armor Performance Evaluation based on European operations. The findings were blunt. Welded construction has proven superior in resisting spall, maintaining rigidity, and enabling rapid repair under combat conditions. In other words, welding had saved lives, not just metal. Crews who once feared rivet bursts, lethal fragments from bolts sheared off by impact, now trusted their hulls. The psychological effect was profound. Sherman crews felt safer, and safety bred aggression. Confidence turned into momentum. By contrast, German tank crews, despite commanding more powerful guns, began to lose faith in their machines. Many complained of brittle armor, rushed manufacturing, and poor field serviceability. Their once superior craftsmanship had been sacrificed to speed. In captured factories at Kassel and Magdeburg, American investigators documented the chaotic state of late-war German production. Panthers assembled in early 1945 showed incomplete welds, gaps filled with hastily poured metal, and armor plates warped from inadequate heat treatment. Under bombing and material shortages, precision had given way to desperation. The contrast was staggering. At Detroit Tank Arsenal or Pressed Steel Car Company in Pennsylvania, Sherman hulls emerged with weld seams uniform to within millimeters. Every plate was X-rayed for microcracks. The industrial discipline that had allowed the U.S. to produce 50,000 Shermans by war's end was the same discipline that had kept those tanks alive on the battlefield. It was a triumph of system over spectacle. The Germans, examining captured Shermans after the war, were candid in their respect. Engineers from Henschel and Mayen, builders of the Tiger and Panther, noted that the American approach prioritized structural integrity and speed of assembly over aesthetic precision. One post-war report summarized it perfectly. Their welding lacks beauty, but exceeds endurance. Even Soviet observers, who toured U.S. production plants under Lend-Lease agreements, were impressed. The Red Army had also adopted welded construction early, but American scale and standardization exceeded anything seen in the East. The result was a fleet that could be repaired faster than it could be destroyed. A logistical miracle Germany could never match. By April 1945, the Allies were advancing through Germany with mechanical momentum no enemy could halt. Sherman columns crossed the Rhine on pontoon bridges, their armor streaked with scorch marks, seams glowing from recent repairs. They looked battered, but they were unbroken. Behind them followed mobile workshops, welding trucks, and maintenance teams that could rebuild a tank in days. To the Germans retreating before them, it felt like fighting a tide that welded itself back together each night. When the war finally ended in May, the statistics told their own story. Of all U.S. armored vehicles knocked out in Europe, over 60% were later recovered and repaired. German recovery rates rarely exceeded 20%. That difference, invisible to the public, defined victory at the operational level. Welded armor had turned America's industrial base into an extension of the battlefield. Every repair depot, every foundry, every factory floor became part of the front line. It was not just a war of steel, it was a war of method, fought in blueprints, workshops, and assembly lines. And that method, proven on the plains of France and the forests of the Ardennes, would soon shape the post-war world. From these welded hulls rose the philosophy of mass-engineered resilience, a belief that quantity, when designed intelligently, could achieve a kind of invincibility. A belief that would define the next generation of tanks and the next era of warfare. In the months that followed Germany's surrender, Allied engineers and analysts fanned out across Europe. into shattered assembly plants, burned-out test ranges, and the rusting remains of the Reich's war machine. Their mission? To understand why the vaunted German armor had failed. They measured weld seams, inspected fractured plates, catalogued penetration angles. What they discovered confirmed what frontline soldiers already knew. Germany had been outbuilt, not just outfought. At the Krupp Steel Works in Essen, Allied inspectors noted how late-war production had degraded. Welding quality varied wildly. Some Panthers bore deep, uneven seams that weakened under strain. In others, metal impurities caused brittle fractures after long marches. By contrast, even a battle-scarred Sherman pulled from the fields of Normandy still displayed clean, solid welds, undistorted by heat or fatigue. The findings stunned many in the German engineering corps. They had prided themselves on precision, but precision without scalability had doomed them. The Americans had proven that perfection did not mean polish. It meant process. When the U.S. Army began evaluating lessons for future design, welding stood at the center. Reports from the Ordnance Department and Aberdeen Proving Ground recommended expanding the method for all armored vehicles. Soon, every tank, from the post-war M26 Pershing to the Cold War's M48 Patton, would carry the legacy of those welded seams forged under fire. Even the Soviets, having analyzed captured American tanks, doubled down on welded hulls for the T-54 and later designs. Welding became a global standard, not because it was new, but because World War II had proven its survival value. In the United States, wartime welders returned home as unsung heroes. They had built the armor that held the line from Normandy to Bastogne. In factories across Detroit, Cleveland, and Chicago, they had joined metal to metal, night after night, often unaware of how many lives their craft would save an ocean away. Some of those welders were women. Rosie the riveters, who, ironically, no longer riveted. They welded. Their hands forged the seams that turned fragile steel plates into living fortresses. By war's end, the U.S. had become the undisputed master of industrialized warfare, not because its tanks were unbeatable, but because they were repairable, replicable, and relentless. Meanwhile, Germany's last surviving panzer crews surrendered machines they could no longer sustain. Their Tigers, mechanical marvels on the parade ground, were abandoned in ditches, too heavy to tow, too complex to fix. At war's conclusion, American intelligence officers compiled a summary of captured enemy documents. Among them was a quiet admission written by a German Design Bureau engineer in 1945, Americans have discovered in welding what we overlooked, the unity of mass and strength. That unity reshaped military thinking for decades. In peacetime research, armor design shifted from mere thickness to structural integrity. Welding allowed better shaping, sloping, and weight distribution. It became the foundation for the Cold War's armored evolution. From the Patton series to the Abrams, everyone an heir to the lessons learned in the hedgerows of France. Yet the legacy was more than mechanical. It was philosophical, a symbol of America's industrial spirit. That innovation wasn't always about invention, but about execution at scale. The welded hull became a metaphor for the United States itself, a structure held together by process, resilience, and the strength of ordinary hands united in purpose. In the end, the German tank crews were not defeated by a superior weapon. They were defeated by an idea that strength could be manufactured by the millions, and that endurance was its own kind of armor. From the wreckage of Europe rose a new order built on that principle, and in every tank that rolled out of a post-war factory, every clean seam, every unbroken weld, the lesson of that brutal contest lived on. That in the heart of war, the power to endure often matters more than the power to destroy. The story of welded armor is more than steel joined under heat and pressure. It is the story of industrial vision, of a nation that realized battles are won not only on the battlefield, but in the factory, the workshop, and the drafting room. In the mud of Normandy, in the forests of the Ardennes, in the frozen fields of Eastern Europe, welded American tanks endured where German machines faltered. They survived punishment not through miraculous design, but through methodical, repeatable production. Every seam told the same story. Resilience was built, not wished for. This quiet revolution reshaped warfare. Tank crews, commanders, and engineers all learned the same lesson. Survival depended as much on logistics and manufacturing as it did on tactics. A well-welded hull could turn a relatively modest Sherman into a mobile fortress, sustaining its crew long enough to influence battles far larger than any single tank. The legacy extended beyond World War II. Welding became the backbone of modern armored vehicles. Structural integrity, mass production, and repairability became guiding principles for decades of military innovation. The Cold War, Korea, Vietnam. Every conflict bore the invisible mark of lessons learned in the crucible of welded steel. But the lesson is not solely technical. It is philosophical. Strength is not inherent in an object, nor in an empire. Strength comes from the ability to combine skill, knowledge, and coordination at scale. America's welded tanks were proof that a civilization could manufacture endurance, outpacing even those who had relied on prestige, perfection, and raw resources. In that sense, the German crews who stared at the enduring Sherman were witnessing more than metal. They were witnessing a civilization's capacity to organize, innovate, and execute. Welded armor was not just a weapon. It was a symbol that in modern war, victory favors those who can create resilience faster than it can be destroyed. And as the war faded into history, the welded seams endured, not just in tanks, but in the industrial philosophy of nations. The lesson was clear. The strength of steel is temporary, but the power of applied ingenuity lasts forever.